This is electrochemistry, the flow of electrons through current provided by matter. Section 1, electrochemical cells. Interpret an activity series and identify the elements that are most easily oxidized and those that are least easily oxidized. Name the type of reactions involved in electrochemical processes. Describe how a voltaic cell produces electrical energy. Describe current technologies that use electrochemical processes to produce energy. Key concepts. For any two metals in an activity series, which metal is more readily oxidized? What type of chemical reaction is involved in all electrochemical processes? How does a voltaic cell produce electrical current? What current technologies use electrochemical processes to produce electrical energy? So welcome to section 1, the meaning of oxidation and reduction. Here's some vocabulary. Electrochemical process, electrochemical cell, voltaic cells, half cell, salt bridge, electro, anode, cathode, dry cell battery, and fuel cells. Connecting to your world. These are animated versions of monster, quote unquote, monster fish that live very, very deep in the sea and produce bioluminescence. On an evening, summer evening, fireflies glow to attract their males. In the ocean depths, anglerfish emit light to attract prey. Luminous shrimp, squid, jellyfish, and even bacteria also exist. These organisms and others are able to give off energy in the form of light as a result of redox reactions. In this section, you will discover that the transfer of electrons in a redox reaction produces energy, and that's key. Connecting to your world. What have you learned that shows that energy can be released in the form of light? When electrons drop from higher to lower energy levels in an atom, they emit energy in the form of light, in the form of electromagnetic radiation. Electrochemical processes. As you have learned, chemical processes can either release energy or absorb energy. The energy can sometimes be in the form of electricity. Electrochemistry has many applications in the home as well as in industry. Flashlight and automobile batteries are familiar examples of devices used to generate electricity. The manufacture of sodium and aluminum metals and the silver plating of tableware involve the use of electricity. Biological systems also use electrochemistry to carry nerve impulses. In this chapter, you will learn about the relationship between redox reactions and electrochemistry. Zinc metal oxidizes spontaneously in a copper ion solution. A zinc strip is immersed in a solution of copper sulfate. B, as the redox reaction proceeds, copper plates out onto the zinc, and the blue copper sulfate solution is replaced by a solution of zinc sulfide. Classify. How can you classify this reaction? It is a redox reaction. Zinc is oxidized and copper is reduced. Study the figure very carefully. Figure 21.1. Question 1, figure 1. What is the color of the copper sulfate solution in figure 21.2a? It's blue. Is the color different in figure 21.1b? It still blue but lighter in color. What is the significance of the lighter color? Blue copper ions have been removed from the solution and changed into copper atoms on the zinc. A spontaneous redox reaction. When a strip of zinc metal is dipped into an aqueous solution of blue copper sulfate, the zinc becomes copper plated, as shown in figure 21.1. The net ionic equation involves only zinc and copper. Zinc plus copper 2 yields zinc 2 plus copper. That's 1 mole of each. Electrons are transferred from zinc atoms to copper atoms. This is a redox reaction that occurs spontaneously. As the reaction proceeds, zinc atoms lose electrons as they are oxidized to zinc ions. The zinc metal slowly dissolves. At the same time, copper ions in solution gain the electrons lost by zinc. They are reduced to copper atoms and are deposited as metallic copper. As the copper ions in solution are gradually replaced by zinc ions, the blue color of the solution fades. Balanced half reactions for this redox reaction can be written as follows. The reduction is zinc metal goes to zinc plus 2 electrons, and copper plus 2 electrons goes to copper metal. If you look at the activity series of metals in table 21.1, you will see that zinc is higher on the list than copper. For any two metals in an activity series, the more active metal is the metal readily oxidized. Figure 21.1 shows zinc is more readily oxidized than copper because when dipped into a copper sulfate solution, zinc becomes plated with copper. In contrast, when a copper strip is dipped into a solution of zinc sulfate, the copper does not spontaneously become zinc plated. This is because copper metal is not oxidized by zinc ions. When a zinc strip is dipped into copper sulfate solution, electrons are transferred from zinc metal to copper ions. Checkpoint. Why doesn't a copper strip that is dipped in zinc sulfate solution become spontaneously zinc plated? Copper is not oxidized by zinc ions. Check out an activity table. Redox reactions and electrochemistry. An electrochemical process is any conversion between chemical energy and electrical energy. All electrochemical processes involve redox reactions. If a redox reaction is to be used as a source of electrical energy, the two half reactions must be physically separated. In the case of the zinc metal copper ion reaction, the electrons released by zinc must pass through an external circuit to reach the copper ions if useful electrical energy is to be produced. In that situation, the system serves as an electrochemical cell. Alternatively, an electric current can be used to produce a chemical change. That system, too, serves as an electrochemical cell. An electrochemical cell is any device that converts chemical energy into electrical energy or electrical energy into chemical energy. Redox reactions occur in all electrochemical cells. Voltaic cells discuss. Remind students of the lemon battery they made in the inquiry activity. Explain that the lemon battery is an example of a voltaic cell. Use its parts to illustrate terms such as cathode, anode, salt bridge, and half cell. Introduce the shorthand method for representing an electrochemical cell. Relate. Italian physicist Alessandro Volta had already been experimenting with static electricity when, in 1780, his friend Luigi Galvani demonstrated that a current of electricity could be generated if two different metals were placed in contact with the muscle of a frog. Volta later showed that animal tissue was not necessary. Current flowed with only the two dissimilar metals. A controversy arose between scientists who believed in animal-generated electricity and those who believed in metallic electricity. Volta settled the matter when, in 1801, he demonstrated his first voltaic cell for Napoleon. The unit of electrical potential, the volt, was named in Volta's honor. Figure 21.2. Volta built his electrochemical cell using piles of silver and zinc plates separated by cardboard soaked in salt water. He used his cell to obtain an electrical current. Voltaic cells. In 1800, the Italian physicist Alessandro Volta built the first electrochemical cell that could be used to generate direct electrical current. Figure 21.2 shows a photograph of Volta's illustration of one of his early cells. Voltaic cells, named after their inventor, are electrochemical cells used to convert chemical energy into electrical energy. Electrical energy is produced in a voltaic cell by spontaneous redox reactions within the cell. You use a voltaic cell every time you turn on a flashlight or a battery-powered calculator. Figure 21.3. In this voltaic cell, the electrons generated from the oxidation of zinc to zinc 2 flow through the external circuit, the wire, into the copper strip. These electrons reduce the surrounding copper 2 to copper. To maintain neutrality in the electrolytes, anions flow through the salt bridge. So we have two electrodes. We have the anode, where you have the zinc going from zinc to zinc 2, and then you have the cathode, where copper is going from copper 2 to copper. Study the illustration very carefully. Figure 3, visual strategy. Explain that voltaic cells can be used as sources of electrical energy because the two half reactions are physically separated. The reaction in the illustration could take place in a single beaker, but it would not be possible to produce a stream of electrons. At which electrode does oxidation, loss of electrons, take place? Oxidation occurs at the anode, or the negative electrode. Where does reduction, gain of electrons, take place? Reduction occurs at the cathode, or positive electrode. What path do the electrons given up by zinc follow? They go through the wire and the electric light to the copper electrode. what happens to the electrons at the copper electrode. And here is the activity series. You can see zinc near the bottom there, and that is going to be above the copper. You see copper down below hydrogen. So that's why zinc will react and copper will not, or copper will reduce. They reduce copper ions to copper. Salt bridge, relate. In discussing the need for a salt bridge in the zinc-copper voltaic cell, explain that as zinc is oxidized at the anode, zinc plus 2 ions enter the solution. They have no negative ions to balance their charges, so a positive charge tends to build up around the anode. Similarly, at the cathode, copper 2 ions are reduced to copper and taken out of solution, leaving behind unbalanced negative ions. Thus, a negative charge tends to develop around the cathode. The salt bridge allows negative ions such as sulfate to be drawn to the anode compartment to balance the growing positive charge. Positive ions such as potassium are drawn from the salt bridge to balance the growing negative charge at the cathode. Constructing a voltaic cell. A half cell is one part of a voltaic cell in which either oxidation or reduction occur. A typical half cell consists of a piece of metal immersed in a solution of its ions. Figure 21.3 on the following page or the preceding slide shows a voltaic cell that makes up or makes use of the zinc copper solution. In this cell, one half cell is a zinc rod immersed in a solution of zinc sulfate. The other half cell is copper rod immersed in a solution of copper sulfate. The half reactions or the half cells are connected by a salt bridge, a tube containing a strong electrolyte, often potassium sulfate. Salt bridges usually are made of agar, a gelatinous substance. A porous plate may be used instead of a salt bridge. The porous plate allows ions to pass from one half cell to the other, but prevents the solutions from mixing completely. A wire carries the electrons in the external circuit from the zinc rod to the copper rod. A voltmeter or light bulb can be connected in the circuit. The driving force of such a voltaic cell is the spontaneous redox reaction between zinc metal and copper 2 ions in solution. The zinc and copper rods in this voltaic cell are the electrodes. An electrode is a conductor in a circuit that carries electrons to or from a substance other than a metal. The reaction at the electrode determines whether the electrode is labeled as an anode or a cathode. The electrode at which oxidation occurs is called the anode. Because electrons are produced at the anode, it is labeled the negative electrode. The electrode at which reduction occurs is called the cathode. Electrons are consumed at the cathode. As a result, the cathode is labeled the positive electrode. Neither electrode is really charged, however. All parts of the voltaic cell remain balanced in terms of charge at all times. The moving electrons balance any charge that might build up as oxidation and reduction occur. How a voltaic cell works. The electrochemical process that occurs in a zinc-copper voltaic cell can be best described in a number of steps. These steps actually occur at the same time. 1. Electrons are produced at the zinc rod according to the oxidation half reaction. Zinc solid yields zinc 2 plus 2 electrons. Because it is oxidized, the zinc rod is the anode, or negative electrode. 2. The electrons leave the zinc anode and pass through the external circuit to the copper rod. If a bulb is in the circuit, the electrons' flow will cause it to light. If a voltmeter is present, it will indicate a voltage. Go back and study figure 3 and see if what is written here makes sense there. Electrons enter the copper rod and interact with copper ions in solution. There the following reduction half reaction occurs. Copper 2 plus 2 electrons yields copper solid, copper metal. Because copper ions are reduced at the copper rod is the cathode, or positive electrode, in the Voltaic cell. To complete the circuit, both positive and negative ions move through the aqueous solution via the salt bridge. The two half reactions can be summed to show the overall cell reaction. Note that the electrons in the overall reaction must cancel. So here are the reactions, the two half reactions. Zinc solid yields zinc 2 plus 2 electrons, and copper 2 plus 2 electrons yields copper metal. So zinc solid plus copper 2 yields zinc 2 plus copper solid. When the zinc sulfate and copper 2 sulfate solutions in the Voltaic half cells are both 1 molar, the cell generates an electric potential of 1.1 volts. If different metals are used for the electrodes, or if different solution concentrations are used, the voltage will differ. Representing electrochemical cells. You can represent the zinc copper voltaic cell by using the following shorthand. So zinc solid slash, or sort of a slash, zinc sulfate aqueous, double slash, copper 2 sulfate plus copper. The single vertical lines indicate boundaries of phases that are in contact. The zinc rod and the zinc sulfate solution, for example, are separate phases in physical contact. The double vertical lines represent the salt bridge, or porous partition, that separates the anode compartment from the cathode compartment. The half cells that undergoes oxidation, the anode, is written first to the left of the double vertical lines. Checkpoint. Which half cell is written first in the shorthand representation of an electrochemical cell? The half cell that undergoes oxidation is written first. Using voltaic cells as energy sources. Although the zinc-copper voltaic cell is of historical importance, it is no longer used commercially. Current technologies that use electrochemical processes to produce electrical energy include dry cells, lead storage cells, and fuel cells. Dry cells. When a compact, portable electrical energy source is required, a dry cell is usually chosen. A dry cell is a voltaic cell in which the electrolyte is a paste. A type of dry cell that is very familiar to you is the common flashlight battery, which, despite the name, is not a true battery. Figure 4, visual strategy. Question 1, describe the difference between the common dry cell and the alkaline battery. In the alkaline dry cell, the electrolyte is a basic potassium hydroxide paste. Figure 21.4, the dry cell and the alkaline battery. Both dry cells and alkaline batteries are single electrochemical cells that produce about 1.5 volts. The dry cell is inexpensive, has a short shelf life, and suffers from voltage drop when in use. The alkaline battery costs more than the dry cell, has a longer shelf life, and does not suffer from voltage drop. Inferring, what is oxidized in these cells and what is reduced? In both the alkaline battery and the dry cell, zinc is oxidized and manganese dioxide is reduced. In such a dry cell, a zinc container is filled with a thick, moist electrolyte paste of manganese 4 dioxide, MnO2, zinc chloride, ammonium chloride, and water, as shown in figure 21.4a. A graphite rod is embedded in the paste. The zinc container is the anode and the graphite rod is the cathode. The thick paste and its surrounding paper liner prevent the contents of the cell from freely mixing. So a salt bridge is not needed. The half reactions for this cell are shown below. Oxidation is the zinc yields zinc 2 plus the electrons, 2 electrons, that's the cathode reaction, and the reduction at the anode reaction is the 2 MnO2, manganese 4 dioxide, plus the 2 ammonium ions plus 2 electrons yields manganese 6 oxide plus ammonia plus water. In an ordinary dry cell, the graphite rod serves only as a conductor and does not undergo reduction, even though it is the cathode. The manganese in manganese 4 oxide or manganese dioxide is the species that is actually reduced. The electrical potential of this cell starts out at 1.5 volts but decreases steadily during its use to about 0.8 volts. Dry cells of this type are not rechargeable because the cathode reaction is not reversible. The alkaline battery shown in figure 21.4b on the previous page is an improved dry cell used for the same purposes. In the alkaline battery, the reactions are similar to those in the common dry cell, but the electrolyte is a basic potassium hydroxide paste. This change in design eliminates the buildup of ammonia gas and maintains the zinc electrode, which corrodes more slowly under alkaline conditions. Checkpoint. What electrolyte is used in an alkaline battery? Well, as stated, it is going to be, well, let's look. The alkaline battery, you have the manganese dioxide in a potassium hydroxide paste. A basic potassium hydroxide paste is the answer. One cell of a 12-volt lead storage battery is illustrated here. Current is produced when lead at the anode of lead 4 oxide at the cathode are both converted to lead sulfate. These processes decrease the sulfuric acid concentration in the battery. Reversing the reaction recharges the battery. Study this very carefully. It'll be very important in the coming slides. And here is another shot of the same figure. You can see that the equation at the anode, you are oxidizing lead to +2 lead, and in the cathode reaction, you are reducing lead 4 to lead 2. Figure 5, visual strategy. Call attention to the grids, 2 containing lead and 2 containing lead-4 oxide. What are the oxidation numbers of the metal lead and the lead in lead-4 oxide? Oxidation number of the elemental lead is 0. The oxidation number of the lead in lead-4 oxide is 4. Which is the anode and which is the cathode? Lead is the anode and lead-4 oxide is the cathode. Let's continue with figure 5. How do you know which is which? Lead can only lose electrons and be oxidized. Lead-2 can gain electrons and be reduced. Write the overall reaction for the battery when it is discharging. Note the products lead-2 sulfate and water, and note that lead is oxidized to lead-2 in lead-2 sulfate. In lead-4 oxide, the lead is reduced from lead-4 to lead-2 and also forms lead-2 sulfate. What is the oxidation number of the lead in lead-2 sulfate? Also, I put a little bit of an illustration there which clearly shows the negative electrode is lead and the positive electrode is lead-4 oxide. And you can see the sulfuric acid in the liquid part of the battery. The charge of the lead in lead-2 sulfate is +2. I also put down the reactions. The lead is oxidized to lead +2 and lead +4 is reduced to lead +2. So you can now clearly see the anode reaction where the lead-4 oxide is going to be reduced to lead-2 sulfate, and at the cathode, the lead, elemental lead, is going to be oxidized to lead-2. Lead storage batteries. People depend on lead storage batteries to start their cars. A battery is a group of cells connected together. A 12-volt car battery consists of 6 Voltaic cells connected together. Each cell produces 2 volts and consists of lead grids, as shown in figure 21.5. One set of grids, the anode, is packed with spongy lead. The other set, the cathode, is packed with lead-4 oxide. The electrolyte for both half cells in a lead storage battery is concentrated sulfuric acid. Car battery. The forerunner of today's car battery was built by the French physicist Gaston Planck in 1859. Planck's first battery consisted of a single cell containing 2 sheets of lead separated by rubber strips and immersed in 10% sulfuric acid. A year later, he presented to the Académique des Sciences a battery consisting of 9 cells enclosed in a box with outside terminals. Planck's invention was significant because it provided the first means of storing electricity. Using the same electrolyte for both half cells allows the cell to operate without a salt bridge or porous separator. The half reactions are as follows. Oxidation is the lead solid, the elemental lead, plus the sulfate yields lead-2 sulfate plus 2 electrons. The reduction is the lead-4 oxide plus the acid sulfate, the sulfuric acid, and plus 2 electrons. And that yields lead-2 sulfate plus water. When a lead storage battery discharges, it produces the the electrical energy needed to start a car. The overall spontaneous redox reaction that occurs is the sum of the oxidation and reduction half reactions. Study these equations and go back and look at the slides that came before. Lead plus lead 4 oxide plus sulfuric acid yields lead 2 sulfate plus water. And then the reverse, lead 2 sulfate plus water yields elemental lead plus the lead oxide or the lead 4 oxide plus sulfuric acid. This equation shows that lead sulfate forms during discharge. The sulfate slowly builds up on the plates and the concentrated sulfuric acid discharges or decreases. The reverse reaction occurs when a lead storage battery is recharged. This reaction occurs whenever the car's generator is working properly. This is not a spontaneous reaction. To make the reaction proceed as written, a direct current must pass through the cell in a direction opposite that of the current flow during discharge. Fuel cells, discuss and relate. Point out that fuel cells were developed for space travel where lightweight, reliable power systems are needed. Fuel cells differ from lead storage batteries in that they are not self-contained. Operation depends on a steady flow of fuel and oxygen into the cell where combustion takes place, and the flow of the combustion products out of the cell. In the case of the hydrogen fuel cell, the product is pure water. Both the electricity generated and the water produced are consumed in space flights. Fuel cells convert 75% of the available energy into electricity, in contrast with a conventional electric power plant that converts from 35 to 40% of the energy of coal to electricity. Fuels other than hydrogen can also be used. For example, ammonia, hydrazine, and methane. Students may be interested in the equations for the reactions that take place in these cells. For instance, for ammonia, 4 moles of ammonia plus 3 moles of oxygen yields 2 moles of nitrogen and 6 moles of water. 2 moles of hydrogen plus 2 moles of oxygen yields 2 moles of nitrogen plus 4 moles of water. 1 mole of methane and 2 moles of oxygen yield 1 mole of carbon dioxide and 2 moles of water. In each case, the products are gases and water vapor, which are normally found in Earth's atmosphere. Divide the class into groups of 3 or 4 students. Have them research the use of fuel cells in the space shuttle and by utility companies. Ask them to prepare posters showing different types of fuel cells and their applications. Where possible, have students include the half cells and overall reactions for each fuel cell. Have them describe the advantages gained by using a fuel cell or fuel cells rather than more conventional sources of electricity. If you are reading this by assignment, we will do that activity. Figure 21.6. The lead-acid battery in an automobile acts as a Voltaic cell when it supplies current to start the engine. Some of the power from the running engine is used to recharge the battery, which then acts as an electrolytic cell. You will learn more about electrolytic cell in section 21.3. In theory, a lead storage battery can be discharged and recharged indefinitely, but in practice, its lifetime is limited. This is because small amounts of lead sulfate fall from the electrodes and collect on the bottom of the cell. Eventually, the electrodes lose so much lead sulfate that the recharging process is ineffective, or the cell is shorted out. The battery must then be replaced. The process that occurs during the discharge and recharge of a lead-acid battery is summarized in figure 21.6. The hydrogen-oxygen fuel cell is a clean source of power. Such cells are often used in spacecraft, predicting what waste product, if any, are produced. Water is the only product of a hydrogen-oxygen fuel cell. As you know, there are many. Fuel cells. To overcome the disadvantages associated with lead storage batteries, cells with renewable electrodes have been developed. Such cells, called fuel cells, are voltaic cells in which a fuel substance undergoes oxidation and from which electrical energy is continuously obtained. Fuel cells do not have to be recharged. They can be designed to emit no air pollutants and to operate more quietly and more cost effectively than a conventional electric generator. Perhaps the simplest fuel cell is the hydrogen oxygen fuel cell, which is shown in figure 21.7 on the following page. In this fuel cell, there are three compartments separated by one another by two electrodes made of porous carbon. Look back at the fuel cell model and see if that makes sense. Oxygen, the oxidizer, is fed into the cathode compartment. Hydrogen, the fuel, is fed into the anode department. The gases diffuse slowly through the electrodes. The electrolyte in the central compartment is a hot concentrated solution of potassium hydroxide. Electrons from oxidation half reaction at the electrode pass through an external circuit to enter the reduction half of the cathode. So it's going to be 2 moles of hydrogen and 4 moles of hydroxide yield 4 moles of water plus 4 electrons. And at the reduction site, 1 mole of oxygen plus 4 moles of water and 4 electrons produce 4 moles of the hydroxide ion, and that's at the cathode. The overall reaction in the hydrogen-oxygen fuel cell is the oxidation of hydrogen to form water. 2 moles of water plus 1 mole of oxygen yields 2 moles of water. Other fuels such as methane and ammonia can be used in place of hydrogen. Other oxidizers such as chlorine and ozone can be used in place of oxygen. The above reaction should be familiar to you. We have used it many times throughout the year. Since the 1960s, astronauts have used fuel cells as an energy source aboard spacecraft. Hydrogen-oxygen fuel cells with a mass of approximately 100 kilograms each were used in the Apollo spacecraft missions. Fuel cells are well suited for extended space missions because they offer a continuous energy source that releases no pollutants. On space shuttle missions, for example, astronauts drink the water produced by onboard hydrogen-oxygen fuel cells. Fuel cells are also used as auxiliary power sources for submarines and other military vehicles. At present, however, they are too expensive for general use. But as the space program continues and they are used more frequently at the high end, they will eventually be not too expensive for general use. Section 2, half cells and cell potentials. Identify what causes the electrical potential of an electrochemical cell. Define the standard hydrogen electrode. Describe how the standard reduction potential of a half cell is determined. And last, interpret the meaning of the sign of the standard cell potential. And those are the 4 objectives for Section 2, half cells and cell potential. The key concepts: 1. What causes the electrical potential of an electrochemical cell? 2. What value is assigned to the electrical potential of a standard hydrogen electrode? 3. How can you determine the standard reduction potential of a half cell? 4. How can you interpret the cell potential of a redox reaction in terms of the spontaneity of the reaction? Let's turn our attention now to some vocabulary and practice pronunciation. Electrical potential, reduction potential, cell potential, standard cell potential, standard hydrogen electrode. Try to use these vocabulary words in discussion in class and when you ask questions. Connecting to your world. Batteries provide current to power lights and many kinds of electronic devices, such as the personal digital assistant shown here in the previous slide. One type of battery that you're probably familiar with is the car battery. The electrical potential between the negative and positive terminals of a car battery is 12 volts. Other common batteries are the ones used to power flashlights, radios, and CD players. They are commonly known as AAA, AA, C, and D batteries. The electrical potential in these batteries is 1.5 volts. In this section, you will learn how to calculate electrical potential. Let's answer a couple of questions on connecting to your world visual strategy. Which of the batteries mentioned is rechargeable? The car battery. Smaller batteries can be rechargeable, but they have to be specially made. Do you use other rechargeable batteries? Students may have experience charging batteries in items such as cell phones, electric toothbrushes, and small vacuum cleaners. Electrical potential. The electrical potential of a voltaic cell is a measure of the cell's ability to produce an electric current. Electric potential is usually measured in volts. The potential of an isolated half cell cannot be measured. For example, you cannot measure the electric potential of a zinc half cell or a copper half cell separately. When these two half cells are connected to form a Voltaic cell, however, the difference in potential can be measured. The electric potential of a 1 molar zinc copper cell is plus 1.10 volts. The electrical potential of a cell results from a competition for electrons between two half cells. A working voltaic cell can be constructed using a lemon and strips of copper and zinc. Figure 8, visual strategy. Check your understanding of electrochemical or voltaic cells by identifying the anode and cathode in the lemon battery. Zinc is the anode and copper is the cathode. What process goes on at the anode? Oxidation. What process goes on the cathode? Reduction. Aha. In which process are electrons lost? Oxidation. What role does the lemon play in the battery? It is the salt bridge. The half cell that has the greater tendency to acquire electrons will be the one in which reduction occurs. Oxidation occurs in the other half cell as there is a loss in electrons. The tendency of a given half reaction to occur as a reduction is called the reduction potential. The half cell in which reduction occurs has the greater reduction potential than the half cell in which oxidation occurs. The difference between the reduction potentials of the two half cells is called the cell potential. Cell potential equals reduction potential of half cell in which reduction occurs minus reduction potential of half cell in which oxidation occurs. So E naught cell equals E naught reduction minus E naught oxidation. This equation is going to become very important in the rest of the section. Standard cell potential. The standard cell potential, E naught cell, is the measured cell potential when the ion concentration in the half cells are 1 molar. Any gases are at a pressure of 101 kilopascals or 1 atmosphere, and the temperature is room temperature, 25 degrees Celsius. The symbols represent the standard reduction potentials for the reduction and oxidation half cells, respectively. The relationship between these values follows the general relationship for cell potential given on the previous page. E naught cell equals E naught reduction minus E naught oxidation. Because half cell potentials cannot be measured directly, scientists have chosen an arbitrary electrode to serve as a reference. The standard hydrogen electrode is arbitrarily assigned a standard reduction potential of 0 volts at 25 degrees Celsius. It would be very important to study this illustration very, very carefully, know exactly what's going on. Figure 9, visual strategy. Have students study the diagram as I instructed. What is the significance of the standard hydrogen electrode, and how is it different from other electrodes? It has been assigned a standard reduction potential of 0 volts at 25 degrees Celsius. What does the standard hydrogen cell consist of? A platinum electrode with hydrogen gas at atmospheric pressure bubbling over its surface. The electrode is immersed in 1 molar acid solution at 25 degrees Celsius. The standard hydrogen electrode is used with other electrodes so the reduction potential of the other cells can be measured. The standard reduction potential of the hydrogen electrode has been assigned a value of 0 volts. The standard hydrogen electrode, which is illustrated in figure 21.9, consists of a platinum electrode immersed in a solution with a hydrogen ion concentration of 1 molar. The solution is at 25 degrees Celsius. The electrode itself is a small square of platinum foil coated with finely divided platinum known as platinum black. Hydrogen gas at a pressure of 101 kilopascals or 1 atmosphere is bubbled around the platinum electrode. The half cell reaction that occurs at the platinum black surface is as follows. The reaction 2 moles of hydrogen ion, aqueous 1 molar, plus 2 moles of electrons yields 1 mole of hydrogen gas, 101 kilopascals. E naught hydrogen ion equals 0 volts. The double arrows in the equation indicate that the reaction is reversible. The symbol represents E naught hydrogen ion, the standard electric potential of the hydrogen ion. The standard electric potential of the hydrogen ion is the tendency of hydrogen ions to acquire electrons and be reduced to hydrogen gas. Whether this half reaction occurs as a reduction or as an oxidation is determined by the reduction potential of the half cell in which the standard hydrogen electrode is connected. What components and conditions are required for a standard hydrogen electrode? The standard hydrogen electrode consists of a platinum electrode immersed in a 1 molar acid solution at 25 degrees Celsius. Half cells. Discuss. Explain that the two half cells of a voltaic cell are competing for electrons and that oxidation or reduction could occur in either cell. The half cell with the more positive reduction potential will win the competition and undergo reduction. Oxidation will occur in the other half cell. The potential produced by the electrochemical cell is the difference in the reduction potentials of the two half cell reactions. Explain that the quantitative value of any half cell potential is obtained by measuring it against the standard hydrogen electrode. Point out that table 21.2 contains tabulated values for some half cells. These can be used to calculate cell potentials. Study all the diagrams very carefully. This voltaic cell consists of zinc and hydrogen half cells. Interpreting diagrams. Where does reduction occur and what is reduced in this cell? Reduction occurs at the cathode. In this cell, hydrogen ions are reduced to hydrogen gas. Standard reduction potentials. A voltaic cell can be made by connecting a standard hydrogen half cell to a standard zinc half cell as shown in figure 21.10. To determine the overall reaction for this cell, first identify the half cell in which reduction takes place. In all electrochemical cells, reduction takes place at the cathode and oxidation takes place at the anode. A voltmeter gives the reading of 0.76 volts when the zinc electrode is connected to the negative terminal and the hydrogen electrode is connected to the positive terminal. The zinc is oxidized, which means that it is the anode. Hydrogen ions are reduced, which means that the hydrogen electrode is the cathode. You can now write the half reactions and overall cell reaction. The oxidation at the anode is 1 mole of zinc yields zinc 2 aqueous plus 2 electrons, and 2 moles of H plus ions aqueous plus 2 moles of electron yields 1 mole of hydrogen gas. So the overall reaction is zinc plus 2 moles of hydrogen ions yields zinc 2 plus 1 mole of hydrogen gas. You can determine the standard reduction potential of a half cell by using a standard hydrogen electrode and the equation for standard cell potential. Now look back at this little mini section and see if it all makes sense. Try to draw some definite conclusions about what's being taught here. In the zinc hydrogen cell, zinc was oxidized and hydrogen ions were reduced. Let E0 reduction equal E0 hydrogen ion and E0 oxidation equals E0 zinc 2 in the standard cell potential equation. E0 cell equals E0 reduction minus E0 oxidation. E0 cell equals E0 H plus ions minus E0 zinc 2 ions. The cell potential E0 cell was measured at 0.76 volts. The reduction potential of the hydrogen half cell is a defined standard. E0 hydrogen ion always equals 0 volts. Substituting these values into the preceding equation will give the standard reduction potential for the zinc half cell. So plus 0.76 volts equals 0 volts minus E naught zinc 2 ions. So the E naught zinc 2 will equal negative 0.76 volts. The standard reduction potential for the zinc half cell is positive 0.76 volts. The value is negative because the tendency of zinc ions to be reduced to zinc metal in this cell is less than the tendency of hydrogen ions to be reduced to hydrogen gas. Consequently, the zinc ions are not reduced. Instead, the opposite occurs. Zinc metal is oxidized to zinc ions. Many different half cells can be paired with the hydrogen half cell in a similar manner. I'll let this run for a few seconds while you look it over. Using this method, the standard reduction potential for each half cell can be obtained. For a standard copper half cell, for example, the measured standard cell potential is 0.34 volts. Copper is the cathode, and copper 2 ions are reduced to copper metal when the cell operates. The hydrogen half cell is the anode, and H2 gas is oxidized to hydrogen ions. You can calculate the standard reduction potential for copper as follows. So you have 0.34 volts equals E naught copper 2 minus 0. Therefore, E naught copper 2 will equal positive 0.34 volts. Now, next up is going to be a table where it gives a lot of the half cell potentials. So this is going to be table 21.2, and it's going to give you electrode half cell reaction E naught volts. So you can see that the values on the far right, and some of the equations will be familiar to you. You can see that the actual defined cell is in the first column next to the numbering. And then you have the chemical reaction and then the E naught on the far right column. Come in very, very handy as a reference sheet for you. Very handy. This value is positive because the tendency for copper ions to be reduced in the cell is greater than the tendency of hydrogen ions to be reduced. Table 21.2 on the preceding page lists some standard reduction potentials at 25 degrees Celsius. The half reactions are arranged in increasing order of their tendency to occur in the forward direction, that is, as a reduction. Thus, the half reactions at the top of the table have the least tendency to occur as reductions. The half reactions at the bottom of the table have the greatest tendency to occur as reductions. For example, lithium ions at the top have very little tendency to be reduced to lithium metal. Lithium is very reactive and it will oxidize very quickly. It will enter into a chemical reaction. Calculating standard cell potentials. To function, a cell must be constructed of two half cells. The half cell reaction having the more positive or less negative reduction potential occurs as a reduction in the cell. With this in mind, it is possible to write cell reactions and calculate cell potentials for cells without actually assembling them. You can simply use the known standard reduction potentials for the various half cells from table 21.2 to predict the half cells in which reduction and oxidation will occur. This information can then be used to find the resulting value. Half cells. Discuss. As students work sample problems 21.1 and 21.2, They may think that when a half-cell reaction must be multiplied by a factor such as 2 or 3, the E0 value must also be multiplied by that factor. Point out that even though 2 or 3 times as many electrons are present, the tendency for the electrons to flow is not 2 or 3 times greater. The tendency, which is measured by the E0 value, remains the same. You're just trying to balance things out. It really has nothing to do with anything else. Point out that until now, it has been assumed that reactions in standard half cells always go in the spontaneous direction. For example, a silver copper cell can be constructed in such a way that the only substance available for oxidation is silver metal, and the only substance available for reduction is copper ions. In this case, the reaction is non-spontaneous and the cell potential is negative. Thus, the sign of the cell potential is an indicator of reaction spontaneity. Students will learn in the next section that non-spontaneous reactions can be driven by an outside source of energy. If the cell potential for a given redox reaction is positive, then the reaction is spontaneous as written. If the cell potential is negative, then the reaction is non-spontaneous. This latter reaction will be spontaneous in the reverse direction, however, and the cell potential will then have a numerically equal but positive value. Now let's look at the last section, section 3, electrolytic cells. The 4 objectives are: distinguish between electrolytic and voltaic cells, identify the products of the electrolysis of water, describe the chemical change that take place during the electrolysis of brine, name 3 ways that electrolysis is used in metal processing. The key concepts: how do voltaic and electrolytic cells differ? What products are formed by the electrolysis of water? What oxidation and reduction reactions occur during the electrolysis of brine? How are electrolytic cells used in metal processing? Let's look at a little vocabulary. Only electrolysis, and it's pronounced electrolytic cell, connecting to your world. DVDs are used to store all types of data, from multimedia computer programs to the latest popular movie. DVDs have made it possible to store large amounts of data in a very small place. To manufacture a DVD, a laser is used to transfer all the necessary data to the master DVD. Then, metal is deposited on the master using electricity. Once the metal disc is removed from the master, it is used to stamp out the duplicate sold to the public. In this section, you will read about electrochemical processes that require, rather than produce, electrical energy. You can see how outdated this book is with the DVDs. They used to be very popular, and they are not around much anymore. I rarely will use a DVD. Connecting to your world, visual strategy. Ask students about the importance of electricity in making and using DVDs. Electricity is needed to deposit metal on the master and also to play the DVD. Students might also recall that the laser used to burn the DVD requires electricity. Electrolytic versus voltaic cells. In section 21.1, you learned how a spontaneous chemical reaction can be used to generate a flow of electrons, an electric current. In this section, you will learn how an electric current can be used to make a non-spontaneous redox reaction go forward. The process in which electrical energy is used to bring about such an electrical change is called electrolysis. Although you may not have realized it, you are already familiar with some results of electrolysis. Silver-plated dishes and utensils, gold-plated jewelry, and chrome-plated automobile parts are a few examples. The apparatus in which electrolysis is carried out is an electrolytic cell. Go back and look at examples of the Voltaic cell and become familiar with them when we look at now electrolytic cells. Figure 21.11, to produce chlorine and sodium hydroxide in electrolytic cells, electricity is passed through brine, a sodium chloride solution. The products have many uses, such as disinfecting swimming pools, cleaning drains, manufacturing soap, and producing paper pulp. Figure 21.12, which I will explain on the next slide, is an illustration of a Voltaic cell on the left, that's A, and an electrolytic cell on the right, that's B. Study them very, very, very carefully. What is the similarity between the two and the difference? So you want to be able to draw these yourself from memory and apply the cells to concepts in electrochemistry. Electrochemical cells can be classified as voltaic or electrolytic. A, on the left, in a voltaic cell, energy is released from a spontaneous redox reaction. The system, or the cell, does work on the surroundings, the light bulb. B, in an electrolytic cell, energy is absorbed to drive a non-spontaneous reaction. The surroundings, battery or power supply, do work on the system, the cell. Comparing and contrasting. How are voltaic and electrolytic cells similar? How are they different? In both the voltaic cell on the left and in the electrolytic cell on the right, electrons flow from the anode to the cathode in the external circuit. In the voltaic cell, energy is released from a spontaneous redox reaction. In the electrolytic cell, energy is absorbed to drive a non-spontaneous reaction. An electrolytic cell is an electrochemical cell used to cause a chemical change through the application of electrical energy. An electrolytic cell uses electrical energy, direct current, to make a non-spontaneous redox reaction proceed to completion. The vast array of electrolytic cells shown in figure 21.11 are used for the commercial production of chlorine and sodium hydroxide from brine, a concentrated aqueous solution of sodium chloride. In both voltaic and electrolytic cells, electrons flow from the anode to the cathode in the external circuit, as shown in figure 21.12. For both types of cells, the electrode at which reduction occurs is the cathode. The spontaneous cell reaction in a lead storage battery provides immediate energy to start a car. Ask students to describe what happens in the battery. Lead and lead-4 oxide undergo a redox reaction in which lead-2 sulfate is formed. Students may have experienced a dead battery. Often recharging can revive a dead battery. Ask what reaction occurs during recharging. Lead-2 ions in lead-2 sulfate are oxidized to lead-4 and reduced to lead. Note that this is a non-spontaneous reaction that requires energy from another source. Electrolytic processes are used to separate active metals such as aluminum, magnesium, and sodium from their salts. The same process is used to recover metals from ores. Compare electrolytic cells to voltaic cells. In both, oxidation occurs at the anode and reduction at the cathode. In the voltaic cell, a spontaneous redox reaction occurs. In the electrolytic cell, external electrical energy makes a non-spontaneous redox reaction occur. All right, let's continue with our discussion and relate. Can metallic sodium be obtained by electrolyzing brine? No. The products are chlorine gas, hydrogen gas, and sodium hydroxide. Sodium is obtained by electrolysis of molten sodium chloride in the down cell. The cell operates at 801 degrees Celsius to keep the sodium chloride melted. The anode and cathode of the cell are separated to prevent recombination of sodium and chlorine. Reduction of sodium ions occurs at an iron cathode. Oxidation of the chlorine ion occurs at a graphite anode. Liquid sodium rises to the top of the molten sodium chloride and is drawn off. Ask students to write the equation for the overall reaction. And there it is. Sodium chloride yields sodium plus chlorine. The electrode at which oxidation occurs is the anode. The key difference between voltaic and electrolytic cells is that in a voltaic cell, the flow of electrons is a result of a spontaneous redox reaction, whereas in an electrolytic cell, electrons are pushed by an outside power source, such as a battery. The redox process in the voltaic cell is non-spontaneous. In the electrolytic cell, the redox process is non-spontaneous. Electrolytic and voltaic cells also differ in the assignment of charge to the electrodes. In an electrolytic cell, the cathode is considered to be a negative electrode. This is because it is connected to the negative electrode of the battery. Look back at the cells that I have listed in figure 12. See if it makes sense. Remember that in a voltaic cell, the anode is the negative electrode and the cathode is the positive electrode. The anode in the electrolytic cell is considered to be positive electrode because it is connected to the positive electrode of the battery. It is important to remember these conventions about the two kinds of cells. Very important. What charges are assigned to the electrodes in an electrolytic cell? In a voltaic cell? Let's think. In an electrolytic cell, the anode is assigned a positive charge and the cathode is assigned a negative charge. In a voltaic cell, the anode is negative and the cathode is positive. Figure 21.13. When an electric current is passed through water, the water decomposes into oxygen gas and hydrogen gas, interpreting photographs. Which electrode in the photograph is the cathode, the anode, and there is the equation for 2 moles of water yields 2 moles of hydrogen plus 1 mole of oxygen. The electrode on the right is the cathode, and the electrode on the left is the anode. Cathodes and anodes. Figure 13, visual strategy. Call attention to the volumes of hydrogen and oxygen that have been collected in the photograph. Why is one volume larger than the other? Well, look at the equation. It's 2 moles of hydrogen plus 1 mole of oxygen. When water is decomposed, 2 molecules of hydrogen are formed for every 1 mole of oxygen. That's the gas, H2 and O2. For emphasis, write the equation for the decomposition of water on the board. Why is it necessary to add an acid to the water in the cell? Water is actually a non-electrolyte. Water is a molecular compound. It does not form a significant number of ions. The liquid in the cell must be an electrolyte. That is, it must contain ions. Remember, pure H2O does not conduct electricity. It's what's in the water that conducts it. Electrolysis of water. When a current is applied to 2 electrodes immersed in pure water, nothing happens. There is no current flow and no electrolysis. However, when an electrolyte such as sulfuric acid or potassium nitrate in low concentrations is added to pure water, the solution conducts electricity and electrolysis occurs. This process is illustrated in figure 21.13. The products of the hydrolysis, the electrolysis of water, are hydrogen gas and oxygen gas. Water is reduced to hydrogen at the cathode according to the following reduction half reaction. Reduction: 2 moles of water plus 2 moles of electron yields 1 mole of hydrogen gas plus 2 moles of the hydroxide ion, and that's at the cathode. Water is oxidized at the anode according to the following oxidation half reaction. 2 moles of water liquid yields 1 mole of oxygen gas plus 4 hydrogen ions plus 4 electrons. That's at the anode. The region around the cathode turns basic due to the production of hydroxide ion. The region around the anode turns acidic due to an increase in the H plus ion. The overall cell reaction is obtained by adding the half reactions after doubling the first one to balance electrons. So there are, I won't read them, there are the equations, and you end up with 6 moles of water goes to 2 moles of hydrogen gas, 1 mole of oxygen gas, plus 4 hydrogen ions and 4 hydroxide ions. The ions produced tend to recombine to form water. So 4 hydrogen ions plus 4 hydroxide ions yields 4 water molecules. For that reason, they are not included in the net reaction of 2 moles of water yields 2 moles of hydrogen plus 1 mole of oxygen. 21.14, the electrolytic cell used for the electrolysis of brine. Interpret diagrams. Which substances are produced by oxidation? By reduction. Oxidation produces chlorine gas. Reduction produces hydrogen gas and hydroxide ions. Now let's answer some questions to analyze figure 21.14. We'll do a visual strategy on figure 14. When water is decomposed, 2 molecules of hydrogen are formed for every 1 molecule of oxygen. Have students study the diagram. What is the purpose of the battery? The battery is a Voltaic cell that supplies the electrical energy needed to drive the non-spontaneous redox reaction in the electrolytic cell. What substance is being oxidized in the electrolytic cell? Chlorine, the chlorine ion. What substance is being reduced? Water. Water is being reduced. Make a sketch of the cell on the board. Use different colors to label the cathode 1 and anode 2 on the battery. Show the flow of electrons from the anode, negative terminal of the battery, to the cathode, negative electrode of the electrolytic cell, and from the anode, positive electrode, and electrolytic cell to the cathode, positive terminal of the battery. Show students that in both the voltaic and electrolytic cell, the definitions of cathode and of anode are the same. Reduction always takes place at the cathode, and oxidation always takes place at the anode. Here is a labeled figure for the question 4, and study it carefully. Everything is fairly well labeled, and a combination of what is written in Q4 and what is labeled in the diagram will help you understand what is required from Q4. Why is a DC current and not an AC current used to run the reaction? DC devices maintain a constant potential difference. The voltage potential from an AC generator alternates in sign. Write the overall equation for the reaction on the board and ask students to use the standard reduction potentials in table 21.2 to show why this reaction is non-spontaneous. So I'm going to do the answer 6 very slowly. You have the oxidation at the anode, and that's going to be the chlorine is going to turn to chloride. That's the oxidation. And that's going to have an E naught of plus 1.36 volts. And then the reduction at the cathode. And that's going to be water plus 2 electrons yields hydrogen and hydroxide. And that's going to have an E naught of negative 0.42 volts. Take your time. So, applying the equation and plugging in appropriately, let's see what we get. So, we get a negative value, you can see, is going to be negative. And it's going to be negative 1.78 volts. So that clears up any possible misunderstanding. Interpret diagrams. This is the same diagram, 2114, and I put this here, the question and the answer, because it's going to be mentioned in this slide. Electrolysis of brine. If the electrolyte in an aqueous solution is more easily oxidized or reduced than water, then the products of electrolysis will be substances other than hydrogen and oxygen. For example, is the electrolysis of brine a concentrated aqueous solution of sodium chloride, which simultaneously produces chlorine gas, hydrogen gas, and sodium hydroxide? The electrolytic cell for the process is shown in figure 21.14. During electrolysis of brine, chloride ions are oxidized to produce chlorine gas at the anode. Water is reduced to produce hydrogen gas at the cathode. Again, make sure that you study all diagrams. This is really a diagram-driven unit. It's going to be diagrams and experiments. Sodium ions are not reduced to sodium metal in the process because water molecules are more easily reduced than are sodium ions. The reduction of water produces hydroxide ions as well as hydrogen gas. Thus, the electrolyte in solution becomes sodium hydroxide. The half reactions are 2 chlorine ions, or 2 moles of chlorine ions, yields 1 mole of chlorine gas plus 2 electrons, and the reduction, 2 moles of water plus 2 electrons, yields 1 mole of hydrogen plus 2 moles of hydroxide ions. The overall ionic equation is the sum of the two half reactions. 2 moles of chlorine ions plus 2 moles of water yields 1 mole of chlorine gas, 1 mole of hydrogen gas, and 2 moles of hydroxide ions. And that, of course, is aqueous. The spectator ion sodium can be included in the equation as part of sodium chloride and of sodium hydroxide to show the formation of sodium hydroxide during the electrolytic process. 2 sodium chlorides plus 2 waters yields 1 chlorine and 1 hydrogen plus 2 sodium hydroxides. When the sodium hydroxide solution is about 10% m over v, it is removed from the cell and processed further. Checkpoint. What is the overall ionic equation for the electrolysis of brine? Well, it would be 2 chlorine aqueous plus 2 water liquid yields 2 chlorine gas plus 1 hydrogen gas plus 2 hydroxide ions aqueous. Anodizing. Anodizing is an electrolytic process for applying a corrosive-resistant oxide coating to aluminum and certain other metals. When an electric current flows through an electrolytic cell containing an aluminum anode, a thin coat of aluminum oxide forms on the surface of the aluminum. Immersion of the aluminum object in boiling water permanently seals the film against corrosion. Dyeing of anodized aluminum can produce metallic red, metallic blue, and a host of other metallic colors on the metal surface. Also, the high porosity of the oxide coating permits it to absorb pigments and lubricants. Fascinating. Anodizing. Using electrolysis in metal processing. Electrolysis has many important applications in the field of metallurgy. Electrolytic cells are commonly used in the plating, purifying, and refining of metals. Many of the shiny metallic objects you see every day, such as chrome-plated fixtures or nickel-plated coins, were manufactured with the help of the electrolytic processes. Electroplating and electroforming. Electroplating is the deposition of a thin layer of metal on an object in an electrolytic cell. An object may be electroplated to protect the surface of the base metal from corrosion or to make it more attractive. An object that is to be silver plated is made the cathode in an electrolytic cell. The anode is the metallic silver that is to be deposited, and the electrolyte is a solution of silver salt, such as silver cyanide. When a direct current is applied, silver ions move from the anode to the object to be plated. So here is the reaction. Pure silver was electroplated onto steel to produce this silver-plated T-set. That's figure 21.15. Plating jewelry. Gold and silver are the most common metals used for plating jewelry. A thin layer of the precious metal is deposited over much less expensive base metals such as copper. Non-metallic objects may be used as the base material as long as their surface is first coated with a conductor such as graphite. Plating solutions contain a suitable electrolyte, an acid or base, to adjust pH. Small amounts of other substances may be added to vary the color of gold jewelry. Nickel, silver, copper, cobalt, and iridium may be deposited along with the gold. The net result is that silver transfers from the silver electrode to the object being plated. Figure 21.15 shows a silver-plated tea set. Many factors contribute to the quality of the metal coating that forms. In the plating solution, the concentration of the cation to be reduced must be carefully controlled. The solution must also contain compounds to control the acidity and to increase the conductivity. Other compounds may be used to make the metal coating brighter or smoother. Electroforming is a process in which an object is reproduced by making a metal mold of it at the cathode of the cell. For example, a phonograph record can be coated with metal so it will conduct a current. It is then electroplated with a thin coating of metal. This coating can be stripped off and used as a mold to produce copies of the record. Electrowinning. In another process, electrowinning, impure metals can be purified in electrolytic cells. The cations of the molten salts or aqueous solutions are reduced at the cathode to give very pure metals. A common use of electrowinning is the extraction of aluminum from its ore, bauxite. Bauxite is impure alumina. In a method known as the Hall-Héroult process, purified alumina is dissolved in molten cryolite and heated to above 1000 degrees Celsius in a carbon-lined tank. The carbon lining, connected to a direct current, serves as the cathode. The anode consists of carbon rods dipped into the tank. At the cathode, aluminum-3 ions are reduced, forming molten aluminum. At the anode, carbon is oxidized, forming carbon dioxide gas. So 2 moles of aluminum oxide plus 3 carbon atoms, or 3 moles of carbon, yields 4 moles of aluminum plus 3 moles of carbon dioxide gas. Study that process very carefully. Electrorefining. In the process of electrorefining, a piece of impure metal is made the anode of the cell. It is oxidized to the cation and then reduced to the pure metal at the cathode. This technique is used to obtain ultra-pure silver, lead, and copper. Other processes. Other electrolytic processes are centered on the anode rather than the cathode. In electropolishing, for example, the surface of an object at the anode is dissolved selectively to give it a high polish. In electromachining, a piece of metal at the anode is partially dissolved until the remaining portion is an exact copy of the object at the cathode. The end.